Okay, all right, we're recording. So we ended yesterday talking about documentation. And I guess before that, we really talked about the model and discretization, right? Breaking the model up, kind of developing this mathematical model and what that takes, right? A lot of simplifications is really the basis of what needs to happen. And then once we've made that simplification, we try and model it as accurately as we can. And as part of that, we want to make sure that we document what we're doing so that we can pass that information on to our colleagues or litigation in case, heaven forbid, there's a litigation against you or within the project yourself. I have been part of a project that had litigation against it. And it definitely helped to have the documentation. We were able to provide our calculations to some third-party reviewers, and honestly, we got positive feedback from those reviewers, all of which were out of state. And so overall, just documentation is a vital part of our kind of thought process or analysis process with utilizing finite elements. It usually includes a number of things. All right, so really it's a description of what we're doing. So we are going to say that it's going to be a description of our mathematical model elements. Sorry, my handwriting. I feel like it's not very good today. I'm having terrible back spasms, but we'll see. Hopefully I'm going to try and make half an hour here. So as part of description of our mathematical model elements, there's all sorts of parts of our model that are part of our that are our attempt to model our mathematical model. So some of those come from, right, loads. There might be special sources to these loads. Maybe there's certain directions we want to define, right? If you're doing an analysis and maybe it's a unidirectional wind loading analysis, everything's symmetrical, right? If you push it on one way and you push on it back the other way, it's going to have the same behavior. Maybe you describe that and say, hey, this is a model. We only put wind on it one direction. We're assuming everything else is equal and opposite. And we moved on from there, right, to simplify things. If we look at our supports, we're going to talk about springs, right? And I mentioned yesterday about, the last lecture about, most of the time, predominantly, and the code allows for this, and we'll get to it when we look into ACI 318 and AISC 360 and some of the specifics about what they tell us to do or some of the guidance they provide for us. They tell us that we can, in some instances, make the grand assumption that our foundations are either fixed or pinned. And as long as we design for that, that's okay. So sometimes, though, we want to maybe incorporate the softness of the stiffness of our soil in the vertical direction. And some of you that have taken geotechnical classes, that is the subgrade modulus of reaction. And so it's really saying how stiff is our spring relative to a square area, right? So if we had 1 square inch and you deflected it 1 inch into the ground, what would be the resistance? A lot of times it's around 200 to 300 pounds, what we would say pounds per cubic inch, PCI. And so we would want to define that, say, hey, we're using springs and we're basing the spring constant on the geotech report or based on the IBC design tables or something like that. But we could define our supports and say, yes, we're using springs, or saying that everything is pinned or fixed, or telling our fixity, etc. And so that's one of the other model elements we would want to define or describe. Our model is going to have members. So those members have materials and releases and other sort of attributes to them. density, thickness, things like that. If they're maybe they're rods or maybe diameters, things like that. That's where I would say that 3D views, back a little bit, 3D views or renderings are very helpful in depicting, right, all of our model elements. And that's what some of this included information here is. Sometimes, I didn't do NaH, Chris did, but we could pull out our Revit structural model like you see here, and maybe we describe some of the beams and columns or just some of the system in general. Maybe you say, concrete on metal deck, right? You could say the thickness, give it the F prime C if you wanted to. You could denote maybe the general materials for everything, A500 grade B or grade C for HSS, some of the tube-shaped columns, A992 for the wide flange, and kind of give a description of some of these things. You could also note in here some of the things that you omitted, right? I mean, if you look at our model between this model, as in our Revit model, structural model, to our actual model here looking in the same direction, right? And I think I mentioned it already. We didn't include the slab on grade, right? Was omitted. We didn't include the foundation elements, right? The piers or the footings that each one of those steel columns were sitting on, right? We assumed that those were largely pinned with some rotational fixity, depending on if they were part of the moment frame or not. You can see this one's part of the moment frame. It has rotational stiffness if we were to push on the frame going in that direction. And that's what supports that edge of the building there, but that first story. But there are things that are omitted. So sometimes maybe you would want to note that in a 3D drawing such as this, right? It's pretty easy to depict. I've seen people, and more summarily, some people would take the Revit model, and you can actually shade and highlight things in different colors and say, this is what I'm including in my model, and this is what I'm not, and things like that. You can see how, as simple as it is, but there are things that are curious about, right? Ignoring, say, this pier and footing, which is sitting, 8 feet below grade. It's got a really tall pier. These piers are not sitting on the, are not sitting as part of the foundation wall. We model the top of the foundation wall, right? And we omit these footings. These are these guys out here, right? That are sitting on an 8-foot tall column with a pier underneath it, right? Does it make sense to model all of that? Maybe it does, maybe it doesn't, right? And so in the hope that the next person that gets to review this model, whoever it may be, they can discern why or why not you chose to do those things. And so it doesn't have to be a novel. I think for the most part, a lot of these, for me, especially in this class, they can be just a one page with a nice detailed rendering or 3D view of your VA model, and then a nice description, right, of what you're using for members and materials, what type of loads you're applying, how you're applying them, where you're applying them, the supports, maybe the fixity, areas or plates if you utilize those, what are some of the properties of those elements as well. So if we go back down here, we're going to add areas. As I mentioned yesterday, there's a huge benefit to using areas. And fortunately, the last time I taught this class, it wasn't a functional, it was functional, but it wasn't functional in an analysis sense in the educational version of VA. And so lucky for us, Adam was kind enough to change those capabilities of VA, so now we can use them and mesh them. So we have areas, right? Areas you can denote span direction, one way or two way, and which direction those are. You can also denote the loading type, right? You can have it load members, or you can have it not load members. You could have it just load nodes, things like that. There's options within VA. Then you have plates, which which might be part of your model, right? Plates are going to have to be some material, which gives them properties and stiffness. We're also going to have to talk about the releases of these plates, etc. Right? All the parameters of the plates, some of the things, all the things that you go down in the project manager tool when you select these elements and you're manipulating, right? Releases, materials, cross-sectional properties, things like that. An important aspect is the intent of the model, right? That's a really important aspect of our model description. What are we using this model for, right? As I mentioned for NIH, we had two models. One was for gravity and one was for lateral. So if someone went through, whether it was a third-party review or someone during construction, maybe someone quit, like myself, right? When I quit more summarily, there were projects that I was working on that were not completed. It wasn't a nice exit. And so, hopefully I did well enough to describe what I was doing at the time, and someone else can pick up where I left off, right? And then I'm no longer there. They can't just call me, even though they did, but they could. It could be, a nasty exit. They don't want to talk to you anymore, sort of thing. And so hopefully you did your job and you described what you were doing well enough that they could pick up where you left off. And so the model is important because someone could open one of those Norm Hall models and be, what the hell is going on here? There's no gravity loads in this whole thing, right? And they'd have no idea that there's a whole separate file. Hopefully you name files. We tried to get into a sign convention at Morrison Merrily, which didn't work out very well, but trying to get pertinent information, because sometimes you have iteration in model. In the model folder for, say, visual analysis, there may be 12 different models. And each one of those could have been manipulated in such a way that we were looking for. Maybe just we were doing chord design or collector design or diaphragm design or gravity or lateral, right? Or a single brace frame on one part of the building. And that could be one model we're running, right? And so being good about describing the title for that and describing that in your calculations is key. So maybe we're doing a lateral analysis. We could do gravity. Or maybe it's a specific element design. Right? And so I'm going through here. I gave you guys the models of Revit models of NIH, just kind of show the changes or the simplifications that are applied from this model we have here to the model you see down here, right? This is structurally, right? What we're including as part of the structural system in this building, right? It's a pretty big difference in components from there to here. And then even further, you look at our structural model, right? There's a lot going on there. There's some of the finer details of drafting. There's all these little posts that are on the that are sticking up above the roof for the PV arrays, and wall assemblies for this penthouse that was sitting up on top of the roof, and things like that. And so here you can see, oh, well, there's a penthouse, but you can't see any of those little members sticking up everywhere, right? You can see all these areas drawn with the span direction specified, and depending on the direction of the deck. You can see how this isn't modeled deeper than the top of our foundation wall. And so, like, all these members are sitting on top of this foundation, and then, it's pinned at the base, right? Sometimes there's fixity on these columns, depending on which direction. So this is just a snippet. And you can see this is volume 4, but only page 3 of 563 of the calculations for Norm Hall, right? So there's a lot of calculations for Norm Hall. And this is just an excerpt that Chris Van Lucien, KDV, that's what that is, copied for me a couple of years ago as just part of, what he went through as his description for the structural model, right? Saying a visual analysis model was conducted using massless materials. And for those of you in Mike's or has taken Mike's dynamics class, you'll understand why these things are massless. For those of you that haven't taken it, when you do a modal analysis, which is what was conducted on NaH as I described yesterday, mass and where that mass is located within the building plays a huge role in the behavior of the building. The mode shapes are really the fundamental frequencies of the building. And then those fundamental frequencies pay into how much mass contributes within each of those frequencies. And then you have to account for a certain amount of the total mass of the structure. And so then based on the deflected shape of those mode shapes, you'll get dominating modes such as the building deflecting, say, in one direction, or translating in another direction, or maybe it rotates, right? And then you have combinations of there too of all the other modes. And so you can see how he describes his member connections, right? Node loaded with the mass is sitting here out in the middle. And then he provided these rigid links. We haven't talked that much about rigid links in VA. Rigid links are just a member element that has infinite stiffness, right? So there's going to be no displacement between this node and this node. It's going to stay the same length. And that this member, unless you release things, is going to have zero rotation about this node and this node. So if this whole assembly rotates, right, each one of these nodes, each one of these 5 nodes, stays in the same space relative to all the other nodes, right, because they're rigidly connected. The beauty about rigid links is it allows us to, say, load an individual node, but then apply the load at other nodes throughout a diaphragm. So what happens is you basically create this cruciform shape in our diaphragm. So there's a single point where Chris would load up this diaphragm, right? So we would load up this center node, right, with some amount of mass, right? And as I mentioned, mass plays into the modal analysis thing. Not a huge deal, but he's loading it here. But in order to get away from, as I mentioned yesterday, about stress concentrations in plates and the fact that when you load a node, that node represents like a very finite point in space. So almost like the tip of a ballpoint pen. And so instead of putting all of this mass concentrated at this very localized point in the diaphragm, we can spread that out using these rigid links. And that allows us to essentially provide mass more centralized to the whole diaphragm instead of this specific location within the diaphragm. And so he talks about why did we do that and things like that. This model description is a little bit more involved because we did a modal analysis, and in that case, it's not as easily it's not as prescriptive. So it requires a bit more attention to the description as to how the designer utilized the modal analysis to create our design. This is another one for Building Z, which is actually the Montana Title building that's off of Garfield behind Morris and Merrily building. This was also done by Chris. So it just talks about lateral force resisting framing, lateral modeling and discussion, loading model and discussion. So, I mean, it just kind of discusses in more detail, how did we load it? Why did we load it this way? What made us do 100% and 30%? For those of you that have been in Mike's class, there's reasons for loading your building seismically in 2 directions at the same time, 100% in one direction, 30 in the other. You will all learn about that when you do take Mike's class next semester if you haven't. And so these are some model descriptions. I wish I had a couple more, and I'm going to try and dig those out, and maybe I'll put them out on D2L for all of you. But I would see for this class, maybe a page, maybe it looks something like this, where you've got some 3D view, ISO views of your model, and you can just annotate on this, describing aspects of your model, how you loaded it, things like that. Maybe there's an additional page behind it that describes things. But I mean, it doesn't have to be as intricate and detailed and as narrative-like as Chris has here. As I mentioned, this was a fairly extreme case with Norm being a modal analysis. And this is just another case of Building Z. But anyway, those are, I would expect that from all of you on the next homework, which I'm planning on getting out there hopefully sooner than later. So let me duplicate this. All right. Boundary conditions. Okay, so we've gotten to boundary conditions. Right, and we've talked about boundary conditions from a theory perspective, right? We would impose these conditions to make sure that we have global stability, right? On top of that, we also use these to ensure we have our behavior matches as close as possible to our mathematical model, right? Relative to connections and supports. So we need to essentially constrain or release the model depending on our mathematical model requirements, and which really come from the real world, right? We're trying to match that and get as accurate as possible. We want to make sure at the same time, though, we're constrained enough that our building, our model is stable, right? And if it isn't stable, then there's some fundamental problem with our real world structure in the first place, right? The architect comes to you and gives you something, and all of a sudden you put it in the model and you're constraining it based on the constraints that they have. Hopefully it's intuitive to you as a structural engineer looking at what they have, that you can see some instabilities at first glance. But if not, some of these more complicated buildings, maybe there's a mode of failure that you don't necessarily see. I think I brought it up before about the field house. One mode of failure, if you were to model the skeleton of the field house, it basically has a bunch of radial glulam beams, like spokes in a wheel, that go up to an oculus, this compression member or compression ring at the top. And then there's a big tension ring around the entire bottom on top of all the masonry walls. That's stable in VA. If you were to model all those spokes of the wheels and put a vertical load on it, it's stable. But the second that you twist that top ring of members just a little bit, all of a sudden it has no lateral support, and that thing would twist and fall to the ground. And there's actually a picture outside Mike and I's office of an example of a dome that was on the East Coast. I think it was in Atlanta, that was being built around the same time as the field house. And so in the field house now, if you go in there and you look up at the ceiling, you can actually see these thin, I think they're 1/4 inch, 3/16 plate steel, strapping steel, that runs diagonal in both directions around the entire perimeter. And you can see it underneath the insulation of the field house roof. And you can see, it's really cool to see that in one direction, those plates have actually buckled. Not a significant amount, but they've pushed away from the roof or the ceiling insulation. And in the opposite direction, they're tight, right? Tight to the ceiling. And so after, somebody went in there and they sawed out the temporary supports for the field house, everything's, settled into place. And luckily those bands were there, because when it did settle, it twisted, and it decided to twist in one direction for one reason or another. And so one direction is tight and the other one's buckled. And so we want to make sure that we capture, right, what's going on, and so that we capture those failure modes when we're modeling, and we capture the real behavior. And so it's used to constrain or release the model. Our boundary conditions are, right, it's really to provide global stability, right? And this all comes way back to when we take the inverse of K, it cannot be singular. We have to, the determinant cannot equal 0, right? And so we don't want it to be singular. If it's singular, it's not stable. We can't solve our fundamental problem, and therein lies an instability. Also, we want to ensure the behavior we're modeling matches as close as possible to the mathematical model. So that's for connections and supports. Right? And we've talked about those in steel design, right? Simple supports versus fixed, fully restrained moment connections. Partially restrained moment connections get a little bit more involved. And we'll talk about that here in a second. Major sources of error or instability in the model come from our boundary conditions, right? So stiffness attracts load, right? Everyone's heard that before. Okay, so over-constraining the problem can result in inaccurate load path, right? So we might have a problem with our model being stable. So we just say, all right, we're gonna fix a couple of these extra nodes. All of a sudden now my model runs, no big deal, we get results, and we're gonna use those results, right? Inadvertently, maybe the fixity in those two nodes do not represent the fixity in the real world. Now all of a sudden you've got a load path that isn't necessarily provided in the real world, and all of a sudden, your model does not represent the real world or really your mathematical model, right? So over-constraining the problem can result in inaccurate load path. Right, fixed versus pinned. Right? We can also release too many degrees of freedom can lead to instability or inadequate load path, right? So we kind of have to find this happy balance or happy medium where we're essentially trying to model as closely as possible the mathematical model, which is a representation of the real world, or the simplification of the real world that we conducted, right? And that we're happy that is adequate in representing the real world, right? So releasing too many degrees of freedom can lead to instability or inaccurate load path. Right? So a pin versus this pinned with a roller, right? And as part of this in VA, right, if you took this pin case, right, and in reality, this pin case, if you put a point load on the center of it in VA, you would get no different results if you modeled it like this, right, with our, like, if you'd get no different results if you modeled it like this versus modeling it like this. And the reason for that is the fact that the whole derivation of all of this is based on small displacement, right, equilibrium, right? So we assume that things aren't displaced. And the fact that we do this in a single step, okay? So, you might be able to do P delta on this, but there is no axial loads that will be developed in this bar. So you would have no instability created based on P delta because of the fact that VA does it in a single step, right? We solve the initial problem and then we add that geometric stiffness matrix. And so because we're taking equilibrium about the undisplaced shape as we see here, right, there is going to be no axial load in this member. But what can happen is if we had this member, and we applied, or we tried to analyze this member and it's pinned. Well, it's also pinned in the axis of rotation, right? Rx, if that was the x direction, right? Well, this would be unstable. Dang, give me a eraser, right? It's unstable in that direction. So we can quickly over-release something, even though we're just saying, hey, it's a pin, but in reality, there is a degree of freedom there that is unrestrained. It can just rotate in thin air, right? And so we would then want to maybe fix the end of this, maybe attach it to a plate or something like that, or fix the boundary condition there where it was a pin so that at least one end of this beam doesn't rotate, right? The other beam can have the ability to rotate, but the other end cannot. We can't have that spinning in space. We talked about that when Adam was in class. So if we look at implementation, all right, these boundary conditions. Well, if we look at nodes, we need to restrain the degrees of freedom at supports. And VA allows you to do that. And this is just a little snippet from the project manager. I think it's project manager tab under the model tab. On the left-hand side, if you picked a node, right, and you wanted to create a support, you can easily do a drop down, right? This is a drop down, and it has some generic specified boundary conditions, right? You could say fixed. If you say fixed, then it automatically puts an X check in each one of these, and these all become fixed. Right? If you do pinned, then it'll go through and it's only going to pin the displacement degrees of freedom, right? And it's going to have all the rotation degrees of freedom free, as you see there, right? So we have dx, dy, dz, rx, ry, rz, right? The rotation and displacement in our 3 coordinate axes. That being the case, right, with these being supports, and I mentioned before, right, with foundational supports, a lot of times the code allows us to, or we can at least rationalize that we can decide between this fixed or pinned support case. Even if it's fixed or pinned, right, with a fixed, that means it is infinitely stiff. The foundation is infinitely stiff for rotation and translation. For a pin, it's infinitely stiff in translation. But is that even accurate, right? I mean, that means each one of these is infinitely So is that accurate? I don't know, right? You would have to tell me. In some cases, I think it's accurate enough, right? Or at least if we could defend it through some code descriptions or discussion, then maybe that's good enough for us, right? If it's not, though, we can impose a support, whoops, that isn't infinitely stiff. I mean, I already talked about this with springs. And VA allows us to do displacement-based or rotation-based based springs, right? All right, so we can say action, two-way. Is it displacement or rotation based, right? We're saying we're applying generated spring support at a single node, right? We can name that spring support for some reason if we wanted to, right? We can make it infinitely stiff if we wanted to. The reason why you would do that is if for some reason you wanted two-way action, or say one-way action, right? Where if you apply load to the spring in one direction, it has a stiffness, and in the other direction, it's free, right? So an example of that would be a slab on grade, right? A slab on grade, the soil provides resistance with the slab on grade like a sidewalk pushing down on it. But if we went out there and picked up the sidewalk with a crane or something, right? The only resistance we have against the crane picking up the sidewalk is the weight of the sidewalk. The soil doesn't hold it down, right? So in some cases, maybe you would want some amount of stiffness in one direction and not in the other. And maybe it's infinite. Maybe you want that. Two-way means that we have the same stiffness in both directions, right? So we have displacement or rotation. We have one-way or two-way. One way would be, right, a slab on grade. Two-way would be, say, like a helical pier. I don't know if some of you have used helical piers before. They're basically a big screw that is driven into the ground with a hydraulic device. And then at a certain torque, it twists off the bolts on the machine used to, screw the the implement into the ground. And at that torque, there's an implied torque to tension or compression relationship. So basically the load bearing capacity of that helical pier in the axial direction based on that applied torque. And they're really awesome. They work great. I've designed quite a few of them. Very easy to design. It comes out of table values. They're proprietary. So we as an engineer, you say, hey, I'm going to support axially in all these locations. You can batter the helical piers. That means you drive them in at an angle. That'll give you some lateral support, right? Because if you drove in all of these screws vertically, right, now all of a sudden there's no lateral restraint at the top that interface with the structure to the soil. And so a lot of times you batter some of those piles to make that work. With respect to displacement or rotation, well, we talked about rotation, right? Sometimes we would want to do rotation for maybe a side plate moment connection, right? I talked about proprietary moment connections like the one on Norm, our side plate. We give our model to side plate. They manipulate it, size the members, beams and columns specifically for our moment frames, and then they input into our model the stiffness of that intersection, which with side plate, it got way stiffer than it would just the two values of our column and beam because we put these huge plates on the sides of our elements. And so we ended up with a big difference in stiffness, and so they needed to adjust that, right? Which we can do that with a rotational spring. If you had a partially restrained moment connection like we talked about in class, right? Well, if we somehow developed through testing or some literature of a connection that was already tested, we could impose what that stiffness is, rotational stiffness is for that member and go from there. Member elements. So similar to nodes, we can restrain degrees of freedom for members, right? So let's say similar to nodes, you can restrain degrees of freedom for members. And these are at the local coordinate level. All right? So we can see all these lowercase values here, right, relative to coordinates. This is really important. I'd say local to global coordinates in any FEA software program is very critical because all of the results we get out of these software programs are based on some coordinate system. Right? And so you got to make sure that you are understanding the results that we're getting out. And so VA can give you local member results, right? Axial forces, shears, but they can also give you global force moments, right? That are applied at a given location in the member, right? Or model. And so you need to be careful that when you go out to get your results, that you're pulling the results that you know are acting at a specific location and in a specific direction. And you can then relate that back to a specific strength, right? In VA, it's helpful because within VA, it also has a design software capability, right? So even in the educational version, the steel design software is a capability. So it'll take all of these shear axial forces, right? Shear in the weak axis and the strong axis, axial load, and then torsion and weak and strong flexure, say in a wide flange section. And it'll go through and it'll take those pertinent design demands in each one of those directions, and it will implement AISC 360, right, through chapter D for tension and F for flexure, E for compression, right, G for shear, and even H for combined loading, and it'll go through all of that and run through all the checks. It'll even be as specific as going through each of the equations, right, or sections pertinent to each one of those checks, so you as a designer can go back and feel confident that they're taking the right values, right? And so it is important that you know what you're releasing. And so here again, you can have, say, a member, we talked about in steel design, but like a shear tab, right? We talked about that in steel design, right? And sometimes that shear tab, maybe we want long slotted holes on the ends of it. And so in that case, we probably have shear transfer in the vertical and the horizontal direction, but we have no axial load transfer capabilities at the end of those members, right? And so in order to properly model that connection, we would probably want to release the axial load on that member, right? So we release, say, axial at one end, right? We wouldn't want to release axial at both ends because now all of a sudden that member can travel, right? It can move. And so I think you would find that if you release the axial load on both ends of the member, you potentially might have an instability in your model overall. So that, I mean, everything is building on everything else, right? Remember, the derivation of released elements right? We calculate a local released equivalent stiffness matrix, then we'll assemble. Right? So you can see is each one of our members. So you look at norm, the model description we had before, right? So we look at norm, each one of these members, right? Each end of the member would have the ability to release any one of these, right? And there's 6 degrees of freedom at each end. There's 12 possible releases, right? We'd want to be careful not to release both ends, as I mentioned, but so you could provide 6 releases potentially or more, and that gets fairly complicated because now VA's got to then take each one of those, knowing that it cannot transfer force in that degree with respect to that degree of freedom at the end of a member. Then all of a sudden it calculates that equivalent stiffness, right? Essentially dumping in that are restrained and are released and fixed degrees of freedom, right? We partition our stiffness matrix and does all of that. And so you quickly realize how powerful VA has to be just to do something very simple. So it is very critical to put thought into the releases, right? It's really easy to check boxes, right? So it's really easy to over-release. Our beam to node interaction. T in there. Got it, Jake. All right, so interaction. And so in here, right, these are the releases for the member itself. That doesn't include the boundary conditions you impose on the nodes that this member end is connected to, right? So member end 1 might be connected to node 1. Well, node 1, maybe you have pinned, right? And then all of a sudden you go and you release, say, the weak axis moment. Well, it's already released, right? Based on the fact that you didn't fix the pin or you didn't fix the node that this member was connected to, right? And so you kind of have to consider the interaction between these member end releases and the nodes themselves, right? It helps to have a 3D, rendering. So it helps to show these releases, right? Show local coordinates and releases. These little circles relate to the moment releases, and I guess they're blocks. You can kind of see the block there. Blocks are regarding forces, right? So you can see these local, I guess those are global coordinates. There would be local coordinates out here. They'd sit something like this, right? Usually I think it is strong shears is Z direction, axial is X. So usually this is X, this is Y, and this is Z for local coordinates. Right-hand rule, X to Y, thumb pointing in Z direction. So we have local coordinates we can show to make sure that we're, properly imposing the end releases. And then also it can depict these end releases. So all of a sudden it's pretty easy to see if all of a sudden we've got all these members framing into this pin, and they're all released, well, that makes sense that this pin there might be an instability there, and our model might not want to run because of it. And so it's good to look through the 3D view. They also have a picture view, right, where they render in the sizes of the actual members that we pick. So if this was a 12 by 22, right, it would show a 12 by 22. It's very helpful when you model angles, because depending on the leg direction, you can have, right, we talked about this in Steel 1, principal axis bending, right, or geometric axis bending. And so depending on where your angle is rotated, you might have one or both, right? One or the other or both. So I'm going to stop there. I think we've made it about 45 minutes or so. And I will talk to you guys hopefully on Friday.